Hello again. Today we're back on the bench with another video about the NanoVNA V2. In this video we're going to be taking a detailed look at calibration standards, adapters, and the measurement plane. A concern that I've raised quite often, as well as any professional RF engineer that's talked to me about this device, has been that it comes with a calibration kit that gives you male SMA standards and a female-to-female SMA adapter as your through standard and a method to connect these guys. So when you make your calibration, you connect the male SMA connector of this cable to the female-to-female adapter like so, taking care to not spin the wire and not spin the adapter and let that go straight in while you spin the outside of the SMA connector. And then when you make a through measurement, you connect this SMA connector right to here for no through standard at all, since this will be your measurement plane. And for each standard, you connect your load, short, and open to the end of this connector. But then when you want to measure common devices, like say this attenuator for example, that have female SMA connectors on them, you're out of luck because you have to remove this adapter to plug that in there. And that moves your measurement plane, which is out here, back to here, but you're calibrated to measure here. So your measurements will be transformed as if you'd placed a negative length of transmission line that's supposedly, well, 50 ohms, but we all know that connectors are going to act a little bit weird and probably not be entirely perfect, or at least not even close to as perfect as a normal transmission line there, like that piece of coax. In his latest video, W2AEW took a look at a feature that the NanoVNA has, that the NanoVNA V2 also has, called electrical delay. This feature is more commonly known in industry as port extensions, or in our case, I guess one would call it a port retraction, since we're trying to move the measurement plane backwards as opposed to forward. This feature allows you to add a delay in pico or nanoseconds, in the case of the NanoVNA, to how long it expects the signal to take to go out to the measurement plane and then to reflect back to be measured by the NanoVNA. So when we add a negative delay, it expects less time for it to go out and reflect, and that effectively moves the measurement plane back along this transmission line. So if we add a small negative delay and disconnect this adapter, we can move our measurement plane to that male SMA connector right there. The problem with this is that it expects that that connector behaves as a perfect 50 ohm, or whatever your normalized impedance is, transmission line, meaning that there's no loss and the impedance, even the real part of the impedance, has to be 50 ohms. In reality, there's probably some connector losses here, and I'm not so confident that a cheap SMA adapter like that actually is a perfect 50 ohms. So we're probably going to see some difficulties there. So the other solution to the problem of the misplaced measurement plane is just to use a female SMA calibration standard. So I found this one on Amazon for about the same price as a NanoVNA, and I figured that I'd compare the measurements I get with this to the measurements I get with this method with no port extension or retraction, and to this method with a port extension or retraction. So in this video, I'm going to be taking a look at a 1-port device and a 2-port device, as well as no 2-port device, just the through measurement, for both sets of these calibration standards. Specifically, we're going to be looking at 4 different calibrations. Why 4 different calibrations? We'll go over what they are real quick. So we'll be doing the normal calibration for this guy for a 2-port calibration with the adapter and the male to SMA standards, and then we just connect this male to the end of this female connector here, so 0 length through connection. Then we'll be taking that calibration and we'll be applying a port extension or a port retraction to it, and we'll take measurements that way. Then we'll be taking a 1-port calibration using the female standards without this adapter here, and then also a 2-port calibration with the female standards, and then the through standard will be just this adapter right here. I want to see if having a through standard in the calibration, especially one that's as cheap as one of these, actually affects its interpretation of measuring a 1-port device, such as the antenna that we'll be taking a look at. For the 1-port device, we're going to be using this printed circuit board antenna with a female SMA connector that I got on AliExpress. Since this antenna is such an interesting design, we'll have a little aside here just to talk about that. The antenna on this board is called a Vivaldi antenna. A Vivaldi antenna is a 2-mode antenna that well, since it has two modes, it obviously has a low and a high resonance. To see what the low resonance does, we have to look at the larger dominant structures on the board, and then the high resonance will come from the smaller structures. So looking at the big picture, we see that this female SMA connector feeds a microstrip transmission line that feeds the right half of this copper with the center conductor and the left half with the ground. If you look at the edge of this, you'll see what appears to be similar to a dipole structure here. So at low frequency, this behaves kind of like a weird-shaped bent dipole. Because it's bent like this, there's probably some modest directionality, but that's considered the dipole mode of a Vivaldi antenna. At high frequency, though, the smaller structure inside of what appears to be a cutout from a feed horn takes over, and this becomes a slot antenna where they've drawn the waves in here propagating out along those arrows, and this becomes highly directional. These antennas find a lot of popularity in Wi-Fi uses because it's not super difficult to tune the low resonance to the 2.4 GHz band, the high resonance to the 5.8 GHz band. Then you have a pretty robust, linearly polarized Wi-Fi solution that isn't as broad bandwidth as, say, a log periodic, which would raise your noise floor by taking in lots of additional RF with its very broadband resonance versus just two tuned resonances in a Vivaldi. This circle down here, you may be asking some questions about. This circle is actually for impedance matching, and I know that that word is tossed around incorrectly and way too often in this industry, but serious analysis of this and the microstrip techniques going on here is probably best left to the numerics on a computer, but we actually do mean it. It's to match the feed point impedance here. It's not a balun, it matches the feed point impedance. Moving on to the two-port device, for that we'll be using just this attenuator board right here. I think I'm going to use the 10 dB attenuator on here, which is just a double resistive pi network and a microstrip transmission line that feeds it. So without further ado, let's get into the 4 calibrations that we need to do, and then take some measurements. Okay, so before we begin our first calibration, it's important to make some notes about the sweep they're going to be doing. It'll be from 100 MHz to 3 GHz using 201 sweep points, the maximum number of sweep points that NanoVNA V2 supports without being connected to a computer. Additionally, because I've been playing around a lot with this display setting, which is electrical delay, we want to make sure that there's no electrical delay applied while we're doing our calibration. So this right now says 0, so that's good. It's in display, electrical delay, and we made sure that that's 0, so all is good. We just put in, make sure that's still 0. And then we're ready to do our calibration. So we go back into the cal menu, smash that reset button, and then we're ready to begin our calibration. For the first calibration, we're going to be doing a normal NanoVNA V2 calibration with the stock cal kit for 2 ports. So with the female-to-female SMA adapter connected snug in there, all good. And then we'll start with our open circuit. We can tell it's open because it doesn't have the pin. So there's our open circuit. Not touching any of the metal, just probably okay to hold the coax. Press the open button. Once that finishes, we disconnect the open standard. You want to make sure that you have the connector in there snug so that when you go to disconnect the open standard, it doesn't start spinning that female-to-female SMA adapter in there. Otherwise, you have to be careful disconnecting it to not spin around the center pin there. Next is our short standard, which has the pin in it, unlike the open standard, even though they otherwise look identical. See, they had the pin in it. And then next is our load standard. So that's done, we can disconnect that. And then finally, our through standard, which is nothing. We just connect the other cable there, press through. And then we press done. And we'll save that in save 0. For the second calibration, we simply remove the female-to-female SMA connector from the male SMA connector at the end of this piece of coax. Then we'll see that instead of a dot at the open circuit for the valid calibration, we'll see this long line here, where it's on the outside of the Smith chart, but clearly an open circuit is being transformed differently over a wide range of frequencies. To fix this, we go into the settings and we hit display. Then we go to scale, then electrical delay, and this is where we're going to put in an electrical delay that makes that look, especially at center frequency, much more like an open circuit. Now, I found experimentally that an electrical delay around 125 or 130 picoseconds is about right. So now it collapses this long line down to almost a point there. The thing that I think is interesting, though, is that if we look at the open circuit, the real part of the impedance here, that's a negative value. And this is what I was talking about earlier, where I asserted that there would be some connector losses going from a male SMA to female SMA adapter that are not going to be represented in this ideal notion of taking a negative length of 50 ohm transmission line. So here we are seeing a large impedance, but a large negative impedance. That's weird. That's pretty weird. It should be a large positive value. But nonetheless, we'll continue, and we'll go ahead and we'll save this new calibration. So we go into Cal, we go Save, and we'll save that in Save 1. Now, just as a point of comparison, because I didn't show in detail that it was indeed a positive value when we had the standard on the other calibration, I'll add this port back, and then I'll place the open circuit standard on it, and we'll look at that on calibration 1 real quick. So here, if we go back and we recall calibration 0, actually, not calibration 1, we can see that that's a dot on the far right of the Smith chart, and that value for impedance is like 6 kilo ohms, fluctuating between a couple kilo ohms actually, and it's positive. So I think losses were not accounted for in doing that port extension, and that's what leads it to having a negative value there. For the third calibration, we'll be doing a one-port calibration on the female SMA standards. So first we'll go into the cal menu, we'll hit reset a couple times, and then we'll hit calibrate, and we'll start connecting our standards. First we start with the open, which has an O on it for open. Once that's done, we'll disconnect that and connect our short. Well, then we'll disconnect that and we'll connect our load. They colored the load differently, and the actual SMA connection seems a bit different here, which seems kind of weird, but should be okay. And press the load button. And for this calibration, we're just doing a one port, so then we'll hit done, and we'll save this in Save 2. So there's our third calibration in Save 2. Next, we're going to go into the cal menu, and we'll see it's waiting for us to add a through standard. So we'll just connect the female to female SMA adapter on both ends. Okay. And then we'll press the through button. And then we can hit done, and we'll save that in Save 3. So now if we go and we recall Save 2, that should look different because we haven't actually calibrated it, and we can see that our through measurement falls off from unity and now has a couple dB of attenuation, which wasn't there when we actually had the valid calibration applied. So we know that those two are indeed different. Here, if I recall 3, it should go up on the through measurement to having basically no attenuation, 0.01 dB, so that's unity. Now for the most tedious part of this whole video, we're going to be making sure all of our calibrations are indeed what we think they are. So we'll go in order, recall them, and check the standards. So first we'll recall calibration 0. Remember, this was the normal stock kit calibration for 2 ports. So here we'll connect our female to female SMA adapter, and then we'll check the open circuit standard. We see open circuit dot. Oh, we have that problem happening where the wrong part wants to come off. There we go. Right part to come off. Make sure that's nice and snug. Short circuit. So we just see a dot. X-axis left side. That's what we see. And our 50 ohm load. Okay. we see a dot in the center of the Smith chart. So it looks like that's good. And we'll check our through measurement on this one because this was indeed a 2-port calibration. So this should look similar to 50 ohms, and our through measurement should read no attenuation here. 0.01 dB, cool, and it's pretty darn close to match to 50 ohms there. So I'd say calibration 0, good to go. Next we'll check our second calibration, which is the one with a port extension. So we'll hit recall here, and now calibration number 1, according to the NanoVNA V2, should see a short standard as a line that looks like it's related to a short on the Smith chart because we effectively added a negative length transmission line there. So that looks right. We'll check our load standard, which would be transformed by that, but should basically still look like a load standard because it's matched, so there shouldn't really be any transformation. Dot in center, so that looks correct. And then finally we have to check our open standard, which should look like a open but transformed with a negative length line, so that looks correct. And then for good measure we can check our new definition of an open, which is nothing connected to the male SMA port, and we see pretty much a dot on the right side of the Smith chart there on the x-axis, so that's all looking good. Next up is to check our 1-port calibration of the female standard, so we'll recall calibration number 2, and then we connect our open circuit female standard here, and we should see a dot on the x-axis on the right side of the Smith chart, and we do. Then we'll connect our short standard, S for short. Cool. That should be a dot on the left side of the Smith chart on the x-axis. That's what we see. And finally we'll connect our load standard. Should be a dot in the center of the Smith chart. And that's what we see, and that's just a 1-port calibration, so we're done there. Next we'll recall calibration number 3, our 4th calibration. And we see a dot in the center of the Smith chart for our load standard, so we won't have to check that again. Then we'll connect our short. We see a dot x-axis far left of the Smith chart, so we're good. Then we'll connect our open. Dot far right x-axis, good. And then finally our through standard, which is just that adapter. Looping the center, and the amount of loss that we see should be basically 0.01 dB. So we're all good there. Looks like the wrong one wanted to come out there. Careful taking this off. Okay. So now that our calibrations are valid, it's time to connect the NanoVNA V2 to our 1-port device. Then I'll show you some screenshots of the NanoVNA V2's actual interface, as well as some Excel sheets with some points that I took out manually, and we'll see how the different calibrations compare. So looking at the pictures of the screen from the NanoVNA V2, we see on the top the 2 done with the stock cal kit, calibration 0 and then calibration 1 with the port extension. And on the bottom, the calibrations from the female cal kit with the 1-port version on the left and the 2-port version, calibration 3, on the right. So the general shapes of all these curves look about the same, but if you start to look closely and inspect edges, or in particular look at the phase plot, things have transformed quite a bit, especially if we look at the port extension where that loop in the S11 graph on the Smith chart has moved from being on the x-axis to being on the y-axis. There's some pretty significant differences going on. And when we go ahead and look at some specific points that I pulled out for these graphs, and we look at them in some Excel charts, it will be much clearer which measurements seem to follow the actual general trend and which measurements are frankly whack. So here inside my spreadsheet I've recorded some values at select frequency points in the sweep done with the NanoVNA V2. I just read them off the interface and then typed them in here manually. Here you can see that I've recorded Z11 parameters in real and imaginary components and the magnitude and phase of S11. Below I've made plots of S11's magnitude and S11's phase versus frequency for all 4 calibrations. Now I made the phase plot because I figured this is where the differences would actually show, but if we take a look at the magnitude plot here, you can see Cal 0 and Cal 1, which were both done with the stock Cal kit. They pretty much follow the same magnitude path, and the same is true for Calibration 2 and Calibration 3, with some minor differences between them, but nothing too significant. Looking over at the phase plot, though, the phase of blue is drastically different from the phase of orange, and those should be basically the same. In the case of Cals 2 and 3, they are pretty much the same, but remember, it wasn't as drastic as applying a port extension there, just adding a calibration for the through measurement. One interesting thing I did find is that the gray and yellow tend to be almost smack in the middle between blue and orange quite a bit of the time. The exceptions are like towards the end here. This isn't exactly in the middle of the two. This is in the middle if you look across the 180-degree boundary, but this one is almost right on the blue. Still, the phase results are definitely quite skewed by doing the port extension method between blue and orange and yellow. If the port extension was correct, then it should pretty much line up with gray and yellow, but it didn't even come close. Another thing to look at that shows that the port extension might not be giving us super reasonable results is the actual impedance values that are measured here. The 1.5 gigahertz is the center of our sweep, and I think that's a pretty good example. Here with the calibration 0, so no port extension applied on the default calibration, we're getting 28.6 minus J 1.45 ohms. If we go and we look at calibration 2 and 3, here we're looking at 30.6 plus J 3.24 and 31.3 plus J 3.8. So, those are ballpark. 30 ohms, almost real. But if you go and you look at the measurement with the port extension, we'll see 36.4. Okay, that's reasonable. Plus J 19.2. That imaginary component isn't even close. And there's quite a number of these in here that are also pretty far off. So here we can see the real component is close to the other one right here. 39.5, 42.1, those are close. 10.1 minus 7.19, those aren't super close. It's almost off by 20. And if we go over here, we'll see that it's minus 5.22 and minus 5.22 at the 2 gigahertz mark. Those are pretty close to the minus 7.19, but 10.1 isn't even close. So we're getting a lot of weird stuff going on with the imaginary component here in at least those two measurements. I certainly don't trust the port extension method based on this, especially at these frequencies. But it's been interesting to take the measurement. Let's move on to the 2-port devices and see how those fared. So if we take a look at the images from the measurements of the 10 dB attenuator here, we see that the female Cal kit standard basically shows us a perfect dot in the center of the Smith chart, whereas there are some differences when we use the stock Cal kit, and we can see that applying the port extension significantly changed the phase of S21. But the overall attenuation that we measure pretty much for the whole frequency range looks about the same. Here in the Excel sheet, we can see about the same thing. There weren't super huge differences in magnitude. See for Cal 0 and Cal 1, there definitely was, not as deep of a resonance with the return loss measurement, but as far as the actual attenuation, they pretty much follow the same trajectory, almost to a T. The differences are less than 0.1, 0.2 dB, definitely. The real difference was in the phase, and we saw that in the Smith chart, indicative of the S11 parameters phase, by the rotation done by the port extension between calibration 0 and calibration 1. Let's take a look at the actual through measurement and see what the differences were. Looking at the pictures of the NanoVNA V2 screen for the frequency sweep, we see the same pattern. The main difference between applying the port extension and not is a shift in the phase, with minimal change in the actual magnitude of the S11 measurement, and there's some general differences between the female and male cal kits between calibration 0 and 1 and calibration 3. So here in my Excel sheet, we can see basically the same thing. If you take a look at the actual magnitudes, these aren't too different. There are some, I'd say pretty significant differences in the S11 magnitude plot where, we're claiming a resonance down near 40 dB return loss with calibration 3, but at 1.5 gigahertz, it's saying it's only 20 dB return loss with calibration 0 and calibration 1. So maybe calibration 3 is more accurate. We don't know. We don't really have a control group here. If we look at the S21 magnitude, which should be unity, so 0 dB. The one that got the highest above unity, meaning the measurement is inaccurate because there's no way that the through measurement itself actually has gain. It's a passive device. At that 0.03 dB figure here, That's the one with the port extension, where I said that if we add the port extension, we start neglecting the losses in the connector. So by neglecting those losses, we force this to be up higher here. And then, as previously discussed, the biggest difference is the phase. When you apply that electrical delay, it moves the measurement plane, and now there's a phase change when measuring your through standard that beforehand was your actual through standard and would show zero phase change. So here we see that very apparent. We applied a port extension, we got a phase change. So as far as the conclusion to this video, we've taken a look at the NanoVNA V2 and some issues with calibration and the actual measurement plane and the calibration kits that are available to us and some of the features that the NanoVNA firmware may allow us to use to try and correct for those issues with measurement plane's location based on the calibration kit that was given to you. This has not been a rigorous, science fair kind of project that has a control group and some standard of truth, but rather just a comparison between 3 or 4 methods of acquiring measurements with the NanoVNA V2 and how different they might be from one another. We've seen that the measurement using no port extension at all, as compared to the measurements using the Female Cal kit, whether you do a full 2-port calibration or just a 1-port calibration, seem to be fairly close to one another. There are some differences, and we know why those differences are. After all, our measurement plane is not in the same spot. But I personally feel that at least the embedded port extension or electrical delay feature in the NanoVNA is not something that I would really use to get accurate measurements. I think you're going to have a much better time if you just take the measurements with your measurement plane being incorrect, and then export an S parameter file using a program like NanoVNA Saver, which now has a port that supports the NanoVNA V2, which I may check out in a later video, or NanoVNA QT, and then do a de-embedding in a program such as Keysight's ADS, or an open source alternative such as QUCS, which should allow you to put in negative length transmission lines and effectively de-embed your circuit, as I did on the amplifier project. That method will almost certainly be more reliable and customizable than the internal electrical delay function on the NanoVNA. Nonetheless, it's cool to know that the function's there if you need to use it in a pinch. I hope you've enjoyed this video. If you liked it, maybe consider smashing that like button instead of the reset button on the NanoVNA calibration, or even consider subscribing for more content. I've got quite a few more NanoVNA V2 videos in particular in the works and scheduled to release already. We'll be covering topics such as antenna tuner topology identification, the differences between a ferrite core and a coaxial cable one-to-one current balun in terms of common mode rejection and frequency response, how to determine the characteristic impedance real portion and the loss of a coaxial cable without access to both ends to plug into your vector network analyzer, and a critical look at Q factor in coils used for crystal radio design. In particular, we're going to take a look at Litz wire versus normal magnet wire and see why that might be advantageous to increasing circuit selectivity and thus the ability to tune different stations, even with just a simple passive resonator circuit. Stay tuned for more updates. That's all for now.